Rules of differentiation part 2. In part 1 we learned that the derivative of a constant is 0 and the derivative of x with respect to x is equal to 1. We also learned that the derivative of a constant times a function is equal to the constant times the derivative of the function. And the derivative of a sum is equal to the sum of the derivatives. I'd like to show you another rule called the power rule. If y equals x to the n power, then dy dx equals n times x to the n minus 1. The exponent becomes a coefficient and then is reduced by 1. We also can express this by saying that the derivative of x to the n with respect to x is equal to n times x to the n minus 1. And x to the n power prime is equal to n times x to the n minus 1. Use the power rule to find the derivative of y equals x squared. The derivative is 2 times x to the 2 minus 1 power, and that simplifies to 2x. Derivatives give rate of change, so it makes sense that the derivative of y equals x squared would give us the rate of change of the graph of y equals x squared. For example, suppose we would like to know the slope of the line that is tangent to the graph when x equals negative 2. The derivative function tells us what the slope is. All we need to do is evaluate the derivative for x equals negative 2. When x equals negative 2, the slope is the derivative evaluated at negative 2, and we get negative 4. So the slope of the line tangent to the graph at x equals negative 2, the slope will be negative 4. When x equals negative 1, the slope is negative 2, still going down but a little bit flatter. When x equals 0, the derivative is equal to 0. We have a horizontal tangent line. When x equals 1, the derivative equals positive 2. The tangent line has a positive slope. When x equals 2, the derivative equals 4. The tangent line has a positive slope and now it's steeper. Suppose a stone is launched vertically upward with an initial velocity of 96 feet per second from the river. The position of the stone measured as the height above the river after x seconds is f of x equals negative 16 x squared plus 96x. Now we actually found the velocity in the last section using the definition of derivative. What we're going to do is we're going to find the velocity again, but this time we're going to use the rules of differentiation. So the velocity of the stone, I used two rules here. First, I pulled out the coefficient, and so I used my coefficient rule. I also used the rule that the derivative of the sum is the sum of the derivative. Then I said the derivative of x squared is equal to 2x, and the derivative of x is equal to 1. When the dust settles, I get negative 32x plus 96, and my units are feet per second. So this velocity function tells me the velocity of the stone at x seconds. If I were to graph it, it also tells me the slope of the tangent line. When time is 0, the velocity is 96 feet per second, exactly what we would expect it to be. At time equals 1, the velocity is 64 feet per second, a positive slope. At 2, 32 feet per second, I see that my velocity is decreasing. I have a flatter tangent line. When I get to time equals 3, my velocity is 0 and I have a horizontal tangent line. When time equals 4, I have a negative slope of my tangent line and a negative velocity. When time equals 5, I have a negative slope, a negative velocity, but I can see that my speed is increasing. I went from negative 32 to negative 64. And then at impact, I'm back to a speed of 96 feet per second, but my velocity is negative 96 because it's going down. If F gives position, and then F prime gives velocity. F double prime, the second derivative, would give me acceleration. So let's find acceleration. This too we found using the definition of derivative, but we're going to use our rules of differentiation. So I use my my coefficient rule, and the derivative of a sum is the sum of the derivative. Then the derivative of x is equal to 1. The derivative of 96 is equal to 0. And my acceleration is negative 32 feet per second squared. Exactly what we would expect it to be. We'll talk more about the rules of differentiation in part 3. Take care.